Okay, the 172 sample final. For the following, based on the table of values for the position of an object in meters and time in seconds. So this is in meters and this is in seconds. And we want to find the average velocity, so that's change in distance or change in time, meters per second, between 0.25 and 1.5. So the change in y is 14.13 minus 6.55 over 1.5 minus 0.25. And that is 14.13 minus 6.55, 7.58 over 1.25 6.064 meters per second is the average speed. Okay. Now we're going to use the central difference theorem to find the slope at 1.5. 1.5, so we're going to go beyond it 1. 19.58 minus 1 before it. 10.36 over the difference. 1.75 minus 1.25. 19.58 minus 10.36 divided by, that's 0.5, and I get 18.44 meters per second is the average slope between those two. So that's probably close to the slope of the tangent line, and the tangent line is f prime at the point we are concerned at, times x minus where we're concerned, plus f of where we're concerned. So we're concerned at 1.5 because that's close to 1.47. So the slope we just calculated is 18.44 x minus 1.50. F of 1.50 is 14.13. And now if I use this to get the value at 1.47, I put 1.47 in there. So I'm going to take the answer I had times 1.47 minus 1.50 plus 14.13, and I get 13.58 approximately. S, the distance at 1.47 seconds, is approximately 13.58 meters. And I've included the units in units with units. If this is the derivative, and I'm supposed to graph the graph, so all this slope is negative. It's negative 3 going to 0. But holding negative 3 at negative, it's negative 3. So I'm going to start up high, going negative 3, and then it goes to a slope of 0 somewhere in here. And it could be any height, but it goes to there. And then it goes up to a positive 3. and then it holds a positive 3. So it's kind of straight in here, straight in there. So it looks something like that. Oops. -3, down 3 for 1, and then it gets less than -3, increases to 0 at 1, -1. So I want to see a minimum there. Goes from going down to going up. And then if I'm graphing the second derivative, which is the slope of this, the slope here is pretty much 0 going to a positive, not quite 1, but close to 1. And it's close to 1 through here, and then it drifts back to 0. Close to no slope, close to a positive slope, close to no slope. Find the equation of the tangent to this curve. So we need to find the slope at 2. So I'm going to find the derivative, which is 6x minus 2. Then f prime at 2 is 12 minus 2, 10. So the tangent line, as we just did, is y equals the slope at the point 2, x minus 2, plus f of 2. So I got to put 2 in there. So that's 3 times 4, which is 12, minus 4, that's f of 2, which is 8. So now we got to use this limit definition to try to find the derivative at 0.5 of this. So we're going to put 0.5 in place of the a, and f, I'm going to type that right into my calculator. X to the x. And then I'm trying to find f, which is y1. I'm going to do fraction in my calculator. Vars, y variables, function y1 of 0.5 plus h, 0.5 plus, I'm going to use x in place of the h there, minus y1 of 0.5. Oop, forgot the parentheses. Parentheses 0.5. Divided by, I'm using x instead of h, and we're supposed to make h be 0.01. So I'm going to my table, and I'm going to try to figure out what y2 is at 0.01. And it works out to be 0.2244. That seems to be f prime, close to f prime at 0.5, a slope of about 0.2244. We can look at the graph and see if it has about a 0.2, 1 to 5, 2 for 10. So it's going to be not very steep graph. At 0.5, it's not very steep in there. I can look closer, but yes, that's the idea. The position of a bob on a pendulum that's swinging back and forth is given by this function, a cosine, which means it's over and back and over. So it goes over 3, and then goes back 3, and goes over 3, because cosine has an amplitude of 3, where the position is given in centimeters and t in seconds. What is the velocity at 0.5 seconds. So if this is the position, the derivative of the position, f prime of t will be the velocity at t, and it's going to be the derivative of this, which is 3. Derivative cosine is negative sine of pi t times the derivative of the inside times pi. That's going to be the velocity. And what's the velocity at 0.5 seconds? So now I put 0.5 in there. Is negative 3 sine of 0.5 times pi is pi over 2 times pi. Sine of pi over 2 is 1, so I get negative 3 pi. This is velocity, and it's centimeters per second. And we can check that, just make sure I'm doing this right. Negative 3 sine pi divided by 2 and that's negative 3 pi, which is, if I want to do it all the way out, times pi. In decimal form, it would be negative 9.425 centimeters per second. Number 6, differentiate. Well, this is a quotient. So I got to take the derivative of the numerator, which is 2x plus 3, times the denominator, minus the derivative of the denominator. Derivative of tangent is secant squared of leaving the angle alone, but then times the derivative of the inside, which is times a 2. So that's the derivative of the denominator, times the numerator, and since it's added, I need to put these in parentheses, over the denominator, squared. And it's fine to leave it like that. This is a product, and the cube root is 1/3 power. So to take the derivative, I've got to take the derivative of the first, which would be 1/3 x plus 1 to 1 less, which is minus 2/3, times the derivative inside, which is 1, times the second, plus the derivative of the second, which is cosine of 2x, times the derivative of the inside, a 2, times the first. And I could have written this to x plus 1 to the 1/3. Tangent line to this, so we have to do this implicitly because we can't solve for the x or for the y. So the derivative of y to the third is 3y squared. Since it's not x, it's dy dx, plus x squared is 2x dx, which is 1, so I don't need it. And this is a product. So the derivative of 3x is 3 times y, plus the derivative of y is dy dx times 3x. So I have dy dx in this one and this one. So I'm going to bring this one over to this side by subtracting this quantity from both sides. I'm going to take this one over to this side by subtracting 2x from both sides. So I'm going to have 3y squared dy dx minus 3x dy dx, bringing this to this side, equals 3y minus 2x. And if I factor the dy dx out of both of these, I get 3y squared minus 3x equals 3y minus 2x. I'm going to divide by this. And now that's gone, and dy dx, my slope of the tangent line, is going to be this with 2 and 2 put in. So if I put 2 in here, I get 6 minus 4, which is 2. And if I put 2 in here, I get 12 minus 6, which is 6. So the slope of this curve at the point 22 should be 1/3. So my tangent line is going to be y equals 1/3 x, and I'm concerned at 2 for the x, plus y at there is 2. Water's being poured into an inverted cone that is 20 feet high and has a diameter of 30 feet, 30 feet across, so the radius is 15 feet. And the water's being dumped in at a rate of, so that's a volume, cubic feet per minute. So dV dt is 3 feet cubed per minute. And I ask, what's the rate of change in the height? So there's some water in here, and they want to know when this is 4 feet deep, how fast is this going up? So we don't want to use this until we get the derivative. So the relationship here is the volume is 1/3 pi r squared h, but I need to relate v to h. So I need to get r out of there somehow. And this has similar triangles. The r in the radius, and this is the height, and that's a triangle that's similar to this one. And I need to get r out, so I'm going to write r over h instead of h over r, because I need to solve for r. R to h is 15 to 20. And the feet cancel, so we don't have to worry about that. And I need to multiply by h on both sides. And this is what I can use for r. 15 over 20, nicely reduced, 5 goes in both. 3/4 h is what r is. So I can rewrite this equation for volume as 1/3 pi 3/4 h squared, so that's 9/16 h squared times another h, so that makes h to the third. Now I have v related to h. I can take the derivative with respect to time, and see, 3 goes to the 9, 3, so I got 3/16 pi, or 3 pi over 16 times 3h squared dh dt. And they want to know the rate the height is changing. And that's this. That's how fast it's going up. When the height is 4, it depends on the height, and so we're going to have to put 4 in for h and divide that into dv dt, which is 3, to figure out dh. So we have 3 feet per minute, cubic feet, divided by 3 pi divided by 16 times 3, 9, I have that, okay, 3h squared, 3 and h is 4 squared, and that will be dh dt. That's kind of messy. The 3's do cancel. 4 squared is 16. That's going to cancel, and I'm going to get 1 over pi is how fast the height is changing with time. So 1 divided by pi is 0.318 feet per minute. It's going up about 0.3 of a foot every minute. Two positive numbers, x and y, always multiply to be 6. So x times y is 6. That makes it a constraint. They have to multiply to be 6. The total of twice the first, so 2 times the first, plus the square of the second, be the total that we're looking for. Find the pair of xy's that minimizes this total. So we need to get this in terms of one letter. So we can either solve for x or solve for y. I probably want to replace, I don't know, let's replace the y, the x. X is going to be 6 divided by y. So this would become 2 times 6 divided by y. That's the x from here, divided by y, plus y squared. And if we want to max or minimize, we find the derivative of this. So that's 12. This is 12y to the negative 1 plus y squared. Derivative of y to the negative 1 is negative 1 y to the negative 2. So negative 12 y to the negative 2 is a y to the positive 2 in the denominator, plus the derivative of y squared is 2y. And so that's d of capital derivative of the total with respect to y. We're going to set that equal to 0, so I got minus 12 over y squared plus 2y equal 0. So if I multiply by y squared all the way through, this times this would be leave me negative 12 plus 2y to the third equals 0. Add 12 to both sides. 2y to the third equals 12. Divide by 2. y to the third equals 6. Take the cube root, and y equals the cube root of 6. And x would be then 6. X would be 6 divided by the cube root of 6. If I put cube root of 6 in for the y and divide it into here, that's x. And y is the cube root of 6. There's the x and y. That makes this total a max or min. Okay. Got to find the limit of this as x goes to 1. So if x goes to 1, 1 squared is 1, 1 minus 1, the numerator would head to 0. ln of 1, if you graph that, you'll see it goes to 0. So they both go to 0, so his rule applies. So I'm going to take the derivative. His rule says if I have to find the derivative of the limit of this, and if they both go to 0 or infinities, then I can take the derivative of just the numerator, which is 2x, and the derivative of the denominator, and then I can put 1 in for those, and neither of these cause a problem. I can put in the 1, and I get 2 times 1, 2 over 1 divided by 1, which is 1, or 2. Now, if I were to graph this, just to check my answer, graph x squared minus 1 divided by ln x. As we get close to 1, what does this look like it's going to? Let's zoom in a little bit. It disappears at 1, but it looks like it's headed towards a height of 2. Okay, find the derivative of this. 3 times 9, 27 x squared plus the derivative ln x is 1 over x. Find the second derivative. Derivative of this is going to be 54x plus, so that's 1 over x. 1 over x is x to the minus 1, so its derivative is minus 1 x to the minus 2. There's the second derivative. To find local max and mins, we set the first derivative equal to 0. So we go 27x squared plus 1 over x equals 0. Multiply through by x. And I got to solve this. And I think it's going to be 1/3, because 1/3 is minus 1/3. Minus 1/3, minus times minus to minus is going to be minus, and 1/3 times 1/3 times 1/3 is 1/27. Times 27 is 1, minus 1, plus 1 is 0. Now, if you don't know how to do that, you can also kind of get the idea of what it is. If we're trying to get 27x squared plus 1 divided by x, graph, and it's 0 at that place. Second, calculate the 0. That's somewhere between minus 1 and 0. Negative 1, enter, 0, enter. I think it's negative 0.5-ish. It says, nope, negative 1/3. So we got the answer to that. This also factors, but I suspect you guys are not real good at that. And so our one and only critical point is negative 1/3. And to find out whether it's a max or minimum, first we need to find out what it is. We can put that into the original function. Probably easiest to go 9x to the third plus ln x. And I just want to put in place of the x's negative 1/3, so I can go to second table and type in negative 1 divided by 3. And there's an error. Oh, yeah, because ln doesn't exist at negative numbers. This doesn't exist there, so there is no max or minimum. Let's take a look at this graph. It goes up all the time. So this looked like it was going to be a critical point, but you can't use negative 1/3 in that. So no max or mins on this one. And you can tell if it's a max or min if you put the negative 1/3 into here, and if it's concaved up, positive value, it would be a minimum. If it was concave down, it would be a maximum, but you can't do ln of negative 1/3, so there is none. Use calculus to find any inflection points. Well, that you set the second derivative equal to 0, which is 54x minus 1 over x squared to the negative. If we set that equal to 0 and multiply through by x squared, I get 54x to the third minus 1 equals 0. So I want 54x to the third to equal 1. Add 1 both sides. Divide by 54. Take the cube root. So we have an inflection point at the cube root of, excuse me, 1 over 54. And if I want the rest of the point, I got to put that into my original equation. That's here, and that is a positive value, so I can find it. There will be an inflection point. Table, plug in parenthesis 1 divided by 54. Cube root is to the 1 divided by 3 power, 1/3 power. And it says it's negative 1.163. That's the inflection point. This is really small, 0.2. If I look back at the graph, at 0.2, this changes from curved down to curved up in there. Hard to see on this graph. Curved down to curved up. I'd really have to expand that to see that. Determine the intervals where f when f is increasing. Well, there's no max or mins, and there's an inflection point, but since there's no max mins, there has to be either always increasing or always decreasing. And since we're putting in only positive x, and we can see it's always increasing, but we can also see that with positive numbers in here, the slope will always be positive. So it's increasing, doesn't exist at 0. So from 0 to infinity, this thing increases. And it never decreases. Determine the intervals where f of x is concaved up or concaved down. Well, if that's the inflection point, And this doesn't exist at 0. Probably from 0 to here, cube root of 1 over 54. It's probably concave down. I'm not sure. This was about 0.2, if we remember. Don't have it there. Oh, I had it here. It's about 0.26. So if I go a little bit closer to 0, 0.2, and put it into the second derivative, it'll tell me whether it's concaved up or down. So I'm going to go 54 times 0.2, close parenthesis, plus a negative parenthesis 0.2 to the negative 2, and that's negative. So before this, between that 0, between 0 and there, the f double prime is less than 0. It's negative, so it's concaved down. And then I want to put something bigger to find beyond that to find out whether it's concave down or up. So I'm going to put something beyond this roughly 0.26. Something beyond that would be something like 1. If I put in, and so it's going to go from the cube root of 1 over 54 to probably infinity. I'm going to check something in there by putting 1 into here. So that's 54 minus 1, which is 53. So f double prime is greater than 0. So it's concaved up. Changes at x equal to this. So between 0 and x equal to this, concave down, putting something in this interval, 0.2 into the second derivative, and we got a negative. Between here and here, 1 is between there and there. We put it in to the second derivative, got a positive number, so it's concaved up. Is there any place where this is not differentiable? And it's not differentiable from negative infinity up to 0 because it doesn't exist there because of the ln. After that, there's no cusp, no fancy. It's just going up pretty straight up. So that's it. Final page. An open top box is made by cutting squares out of the corners of a sheet of cardboard that's 3 feet by 4 feet. Going to cut a corner out here, corner out of there, corner out of there, corner out of there. Each one of these corners is a square. They're going to be all the same size, so I can put X's on all of them. Dotted line where I'm going to fold. Going to fold this up. This is going to be gone. This is going to be gone. Fold that up. Fold this up. Fold this up. And I make a box that has a volume that's equal to the length, which is 4 minus an x and an x. 4 minus 2x. The width, which is 3 minus 2x. 3 minus x minus x. 3 minus 2x. And a height that is, well, I fold this x up, it's going to be x high. So now I want to find out what will maximize this. So I'm going to set the first derivative equal to 0. Well, I can use the product rule on this. It's kind of messy when you got 3 of them. So first I'm going to multiply this. 4 times 3 is 12. 4 times minus 2x minus 8x. Minus 2x times 3 is minus 6x. Minus 2x times minus 2x is plus 4x squared. I got to take that times x, so that's 12x minus 8x squared let's see, minus 14x minus 8x, and minus 6x is minus 14x, and then times an x is x squared, plus 4x to the third. So the derivative is 12 minus 28x plus 12x squared. That's a quadratic. We can use the quadratic formula. We can try to factor it. See, there we could take stuff out. 4 goes into all those. That would be 3. Let's just put them in order. The x squared first. 3. 4 times 3 is 12x squared. 4 times 7 makes negative 7 makes negative 28. And 4 times 3, I think that factors. 3x, maybe not. And if I put 3 there and x there, that's 9 minus, not going to make, that would have to be a 1, so that's 9 minus, no, they both have to be minus. So it doesn't factor. So I can use the quadratic formula to solve for this. So minus b plus or minus the square root of b squared minus 4 times a times c, 9 times 4 is 36, all over 2a. 49 minus 36 is 13, so 7 plus the square root of 13, or 7 minus the square root of 13, both divided by 6. Could be possibilities, but I think, are they both positive answers? And we're supposed to find the maximum volume, so we could put these into the second derivative, but let's just graph it. Parenthesis, clear. Parenthesis 4 minus 2x, 3 minus 2x times x, graph, and there's an answer there, there, and there. Oh, we're looking for the max or minimum, so there's a max and there's a min. Let's see, the max, this min is negative, so we don't want that. There's a max here, and then it goes on forever, but we can't fold that sizes. So it's going to be this one, I believe. It's got to be around point something. So I can calculate the max. That's between 0 and 1, and I think it's about 0.5, and it says, no, about 0.56. 0.5657, which I think is what this is. Parentheses, 7 minus the square root of 13 divided by 6, and that is that one. This one we can't get there, and that'll be a minimum anyway. All right, final question. Sketch a curve that has these characteristics. It is defined and differentiable from minus 6 to 6. It has 2 points where the first derivative is equal to 0, one at x equal 2, the slope equals 0, and at minus 2. So slope of 0, slope of 0. Has a y-intercept of 0, negative 2, an x-intercept at 4, 0, And the second derivative is negative between -2 and 0. So it's for here, it's got to be concave down. And positive between -6 and -2. So it's got to be concaved up in here. And between 0 and 4, it's concaved up. 0 and 4, concaved up. And it is 0 on 4 to 6. So it's straight. No curvature. So it could be straight going up, straight going down, or straight going across. Something straight. First derivative is positive from 2 to 6. So from here to here, it has to be increasing because the first derivative is positive. Otherwise, the rest of the time, it's decreasing or not increasing. It could be decreasing or going flat. The curve has an absolute minimum that is also a local minimum, the absolute maximum is not the local maximum. There's no local maximum. Okay. It has to hit here. It's concaved down. And let's see. On the interval -2 to 0, the second derivative is negative. What's the first? First derivative is positive over here, and the rest of the time it's decreasing. So it got to be going down, concaved up to here, then concave down, and then it's 0. Oh, and it's got to have a slope of 0 right here. So concaved up, going to a slope of 0, then concave down, and then it's still decreasing, but it goes to a slope of 0 here. And then the rest of the way, it's got to be increasing, concaved up, and then straight. So I'll just continue straight. And it's supposed to have an absolute minimum. That would be down here. It has a local minimum, which is also there. Has an absolute maximum. Yeah, there's a high spot here and a high spot here, but they're not local maximums. So there's no local maximum. So this would work for the graph. That's a tricky one. It takes a lot of thinking to get through all that one.